Good afternoon, students. Today we'll study about the modern physics, in which we are going to be study about this photoelectric effect. What is photoelectric effect, and we are going to be study about the Compton effect and all those things. So about the matter waves also we are going to be study today. So first we will see what is photoelectric effect, then what is Compton effect, and what is dual nature of light. All those things we are going to be study today. So first of all, we'll see the what is photoelectric effect and all those things. So first of all, if you see the maybe in the late minute. So we are going to be study about today what is photoelectric effect and all those things, and as well as the about what we call the matter waves. About the matter waves we are going to study. So maybe in the late 19th century and as well as in the early 20th centuries, some revolutions has been taken place in the physics. So what are those means? And classical physics like a Newton mechanics has been developed, and this Maxwell's electromagnetic theory had achieved remarkable success in explaining the wide range of phenomenon. So, however, some experimental observations emerged that they explained this the classical explanations has been defied, leading to the what we call quantum mechanics. Okay, so if you take about this photoelectric effect was discovered in the year 1887 by the scientist Hertz. So he presented one of the most puzzling challenges. So when light shines on certain metal surfaces, electrons are going to be ejected. Okay, that means when a light is falling on some metal surfaces, electrons are going to be ejected out. So this phenomenon, the classical waves theory of light could not explain, whereas what we call Einstein's explanation in year 1905, which introduced the concept of light is in the form of a quanta, that is light quanta, which we call it as a photons. So he earned a Nobel Prize for that one. So which changed what we call understanding of light. Okay, then Compton effect came in the year 1923. He provided that further evidence of the light behaves as a particles, demonstrating that the X-ray scatters of electrons like uh, X-ray X-ray scatters of electrons, which measurable changes in the wavelengths. That means whenever they are scattering, you are going to get different types of wavelengths. It is original length it is having, and as well as in addition to the original some wavelength you are going to be happen. Okay, then after de Broglie's explanation has been came in the year 1924, who proposed that light can be exhibit particle properties, then matter should be exhibit wave properties. Okay, so that means for both it is having both wave nature as well as the particle nature, which was proven by some scientists Davison and Germer, and as well Davis and Germer independent. Then after got this what we call Thomson and Reed, they have given the explanation for the particle nature as well as the particular wave nature of the light. Then after they have developed in the year 1927, Heisenberg developed uncertainty principle. Okay, that is both the pair you are going to be have. So now if you see about the photoelectric effect, first of all, what is photoelectric effect we have to see. So photoelectric effect is the phenomenon in which the emission of electrons from a metal surface when electromagnetic radiation uh, falls upon it. That is nothing but when the electromagnetic rays is hitting on a metal surface. So like this, if we are having any metal surface, these are the electromagnetic rays. So generally this electromagnetic radiation, particularly we are going to be take like what we call UV rays or visible light. Okay, UV or visible light. This UV visible light, UV or visible light, whenever it is hitting the metal surface, it is going to be emits the electrons. Okay, which is going to be emit the electron in this fashion. So these emitted electrons, will be calling it as a photoelectrons. We are going to be called here. Okay, photoelectrons we are going to be called. So generally, if you see the experimental setup for this one, generally you are going to be have a evacuated glass tube. Okay, you are going to be have the evacuated glass tube. You are going to be have, in which it is going to be containing two electrodes. It is going to be have. Okay, so in an evacuated glass tube, we are going to be placed two electrodes. We are going to be placed. So one is the emitter, that is cathode, the metal surface to be illuminated, and another one is the collector, which is the anode. So electrode to collect emitted electrons. Then we will be having the variable voltage source. We are going to be have to apply the potential difference between the two electrodes. To apply the potential difference, we require this variable voltage sources we require. And also we'll be having in this setup ammeter you are going to be have, so which measures the current, that is the photoelectric current, it is going to be measured. And we require one source which is a monochromatic light source you are going to be have, so with variable frequency and as well as the intensity you are going to be have. So when we take this light that is from the source, which is having different frequencies as intensities, which is going to be fall on the metal surface, which is called it as a emitter, or cathode we are going to be called, and the collector, which is having the electrode to collect the emitted electrons. Okay, which after getting the electrons, it is going to be shown in the what we call ammeter, reading as the flow of electrons, that is in the form of a current. It is going to be shows the reading. Okay, so this is what experimental setup you are going to be have. Okay, so if you want to see in detail about this experimental setup of this photoelectric effect, you are going to be have what we call evacuated glass tube you are going to be have, in which we are going to be have the two electrodes, and one source will be there, and this source will be producing the electromagnetic radiation, which is going to be fall on this what we call metal surface, which collects this so what we call electromagnetic waves, and after that it is going to eject the electrons. So that ejected electrons, the number of electrons whichever they are ejected, that will shows a reading in the ammeter which is connected. So that is what experimental setup you are going to be have. And the experimental observation after doing this after doing this photoelectric effect experiment, so the observation of photoelectric effect, the experimental observation of the photoelectric effect, what you are going to be have is mainly it is going to be have some things. So that is first one which we see in this, the first observation in which we are going to see is for a given material. Okay, for a given material, that means whatever may be the metal surface whichever we have placed, for a given metal surface, there is a minimum photon energy, that value will be h nu naught, we are going to be called. Okay, h nu naught. Okay, for a given material, there is a minimum photo energy h nu naught, which is the characteristic of the material. Which is the characteristic of the material. So no photoelectrons would be released by radiation less than nu naught, called as a threshold frequency. So if the what we call the light which is falling onto the metal surface, which is having the frequency, the radiation frequency, if it is having less than the value of nu naught is a particular value, less than that frequency if we are having, which we calling it as the threshold frequency, the incident radiation which is having the frequency less than nu naught does not produce any photoelectrons. That is what they have observed. Okay, the incident radiation, it should have the frequency more than this, greater than nu naught. Then only it is going to be give the photoelectrons. That is one observation they have seen, right? So similarly, the second observation which they have seen by observing in this experimental presentation is the kinetic energies of the emitted photoelectrons shows an energy distribution that ranges from 0 to a sharp energy maximum, K maximum. Okay, so the second observation they have seen in this is the kinetic energies. Okay, the kinetic energies of the emitted photoelectrons here. The emitted photoelectrons shown an energy distribution ranging from 0 to a maximum of K maximum. Okay, K maximum you are going to be on. So the value of K maximum depend upon the incident photon energy and the work function of the material. Okay, work function of the material independent of light intensity. Means it does not depends upon the light intensity, but it depends upon the incident photon energy only. It depends on photons energy only. Next, they have seen that the photoelectric current is directly proportional to the light intensity. The photoelectric current is directly proportional to the light intensity. That means if you increase, if you increase the intensity of the light which is falling on the metal surface, automatically the electric current which we call it as a photoelectric current is going to be more. That means it is directly proportional to the light intensity which is falling on the metal surface. If you increase the intensity of the light, then automatically the what we call photoelectric current is also going to be increases. Okay, photoelectric current is also going to be increases. So that is one point they have observed. And then the photoelectric emission. Okay, the photoelectric emission phenomenon is instantaneous. The photoelectric emission phenomenon is instantaneous. That is, there is no time lag between the irradiation and the emission. That means whenever the electromagnetic radiation, which is UV or visible, whatever it may be, which is falling on the metal surface, immediately you are going to be the electron. That means there is no time delay in between the incident of these photons and as well as emission of these photoelectrons. Okay, so that is one thing they have observed. Okay, and one more thing they have observed is the phenomenon is random phenomenon. At any particular instant, only one among millions of atoms of the metal will emit the photoelectrons, right? Photoelectrons. And if you see, the classical electromagnetic wave theory of radiation is found incapable of explaining the above mentioned points here. Okay, the above mentioned points, whatever the points whichever we have mentioned. So these are not explained by the classical theory of the electromagnetic radiation. Okay, classical theory of electromagnetic radiation. These are not explained by what we call classical theory. So these are some points with the help of this particular photoelectric effect. So mainly the things they have observed is one is effect of the intensity of light. So effect of intensity of light. That means if you increase the intensity of light, automatically the current which is coming out, that is number of photoelectrons which are coming out, will be increases. That means the photoelectric current is directly directly proportional to the intensity of incident light. That is the effect of incident effect of intensity of light, we can say here. Okay. Next, effect of frequency of light. That means, as we have explained here, if for each metal there exists a threshold frequency, that is nu naught we have called. So below this nu naught, you are not going to be give any photoelectrons. If it is greater than nu naught, then only you are going to be get the photoelectrons. Okay. So above threshold frequency, the maximum kinetic energy of the photoelectrons increases linearly with frequency. That is what we have. The photoelectric current is instantaneous. That is, as I told that whenever the light is falling onto the metal surface, immediately it is going to be produced the photoelectron. That is, the current is going to be produced here. So the photoelectric current is instantaneous. You are going to be have. So electrons are emitted within the time period. Means there is no time delay. Maximum around 10 to the power of minus 9 seconds. After that, they are going to be illuminate the photoelectrons. That is what you are going to be have. And one more thing is you have effect of applied potential. That means when positive potential is applied to the collector, photoelectric current increases initially, and then saturation you are going to be get. That means if you see this point we didn't explain. So here, if you take this is the V, the applied potential, the positive potential is applied to the collector. So if you increase this V value, so current is going to be increases and come to the saturation region, and it is going to be keep constant. Okay, effect of the applied potential we can say here. So when positive potential is applied to the collector, photoelectric current is going to be increases initially, and then saturation will going to be come here. Okay, and similarly when negative potential is applied, current decreases. Okay, when negative potential is applied, the current is going to be decreases here. Okay, so the stopping potential is related to the maximum kinetic energy. That is in terms of kinetic energy maximum is equals to EV naught you are going to be have in terms of it. And next is nature of metal surface. So different metals have different threshold frequencies. Okay, different metals you have different threshold frequencies. Like if you take alkali metals, that is alkali metals means which are made up of like a sodium, potassium, or cesium, have low threshold frequencies and are photoelectrically sensitive to visible light. Most metals require ultraviolet light for photo emission. That is what these are the observations which are observed after performing this photoelectric effect experiment. Okay. If you go for a classical theory, what are the failures which we have in the case of the classical theory? We'll see here. Okay, the failures which are there in the case of the classical theory. So mainly the failures of classical theory here. Failures of classical theory. So, classical electromagnetic theory predicted that energy should be dependent on intensity. This energy should depend on intensity. Depend on intensity. That means what it means energy should depend on intensity means if here the intensity should give the electrons more energy. Okay, that means if intensity is higher, okay, intensity value is higher, then it should give electrons more actually. That means the intensity is more, electrons is more. Intensity is more, the number of electrons which are coming, that is photoelectrons, whatever it may be, which are coming should be more. But this was not observed experimentally. Means even though if you are increasing the intensity of incident radiation, there are no observation that more number of electrons are emitting. Okay, which is not observed. And in this case, classical theory fails to explain about the what we call no threshold frequency. This is failed to explain the what we call the second one, which is a no threshold frequency. No threshold frequency. So any frequency should work if intensity is high. Okay, any frequency should work if intensity is high enough. That means according to the classical theory, what they say is if intensity is more, automatically the number of electrons which are coming out should be more, but that is not observed here. So the experimental observation, it contradicts, okay, contradicted by the experiments which they have performed. And according to the classical theory, they says that time delay is expected. Time delay is expected. time delay is expected. That means electrons should accumulate energy over time before ejection. But what will happen is emission is instantaneous. That is what we have seen in the case of this. So these are the failures according to the classical theory. So these failures demanded and fundamentally new approach to understanding this light and matter interaction. Okay, so this is what we have. After this, we have got what we call Einstein's explanation for this photoelectric effect. So photoelectric effect was performed by Hertz. So he given some assumptions, but later on, Einstein explained this photoelectric effect, which we will be calling it as a photoelectric effect. Einstein's explanation we are going to be called here. So what actually this Einstein done is mainly he got the quantum hypothesis. Okay, he got the quantum hypothesis. So in the year 1905, Albert Einstein proposed a revolutionary expression, otherwise explanation, based on this what we call Max Planck's quantum hypothesis. Based on Max quantum hypothesis, he given what we can proposed a revolutionary explanation for this one. Okay, so Einstein suggested that light consisting of discrete packets of energy. Discrete packets of energy. According to the classical theory, the light is continuous. Okay, the light is continuous, but Einstein explained that the light is not continuous, but it is consisting of discrete packets of energy, which we are calling it as a quanta or photons we are calling. We'll be calling it as what? Quanta or photons we are going to be called. So he got the Einstein got a new proposal that the energy is not in the form of, the energy is not continuous, but it is in the form of discrete packets of energy it is having, which they will be calling it as a quanta or photons they have called. So if you see the Einstein's postulates, okay, Einstein's postulates. So who explained this photoelectric effect based on Max Planck theory? So he given some postulate, which we call it as the Einstein's postulates. We are going to be called. Okay. So first postulate which we have is light consists of photons. Light consists of photons. Okay. He says that the light is in the form of discrete packets of energy, which we are calling it as a photons. He says that these are going to be, that means the photons are going to be carry some energy, which he given that the energy E should equals to h nu. E should be equals to h nu, where h is the Planck's constant we have and nu is the frequency of light. The Planck's constant value is 6.624 into 10 to the power of minus 34 Joule seconds. And nu is the frequency of light which is incident. So that is the first postulate of Einstein, that is light consisting of photon. Right. So next one, the proposed postulate from Einstein in the case of the photoelectric effect is one photon interacts with one electron. Okay. One photon interacts with one electron. One photon interacts with one electron. According to Einstein, he says that in the photoelectric effect, one photon is completely absorbed by one electron. One photon is completely absorbed by the one electron. That is the second postulate which is given by Einstein. And another postulate which is given by Einstein in the case of this photoelectric effect is that is the work function concept. Work function concept. Right. So what is work function concept here? It is required a minimum energy. It is required a minimum energy, which we will be calling it as a work function, which is calling it as a work function. So generally denoted by W or phi or W, is required to liberate an electron from the metal surface. A minimum energy called work function is required to liberate an electron from the metal surface. So these are the three postulates which are given by the Einstein for this photoelectric effect, okay, which we will be calling it as the Einstein's photoelectric Einstein's explanation of this photoelectric effect we are going to be calling here. Okay, suppose if you take here we can get the Einstein's photoelectric equation. So suppose if a photon of energy h nu, okay, a photon of energy h nu is striking the metal surface. So what is photoelectric effect? The incident radiation is falling on the metal surface, which is having the suitable wavelength. Then it is going to be eject the electron. So here we will be taking the photons having the energy h nu, they are striking the metal surface. So this h nu value should equal to pi plus Ke maximum. This energy can be given as h nu is equal to 5 plus Ke maximum we can keep. Okay. So here, this we can write h nu is equals to phi is equals to, we can write it as h nu naught. Why we are writing h nu naught? Because nu naught is the minimum frequency which is required to produce the photoelectrons. So, and this energy, kinetic energy will be half mv square maximum, half mv square maximum you have. So this is what the photoelectric equation, Einstein's photoelectric equation. Here h nu is nothing but the energy of the incident photon. H nu is nothing but the energy of the incident photon, and phi, which we have written as h nu naught. So phi is equal to h nu naught, which is called it as a work function of the metal. And nu naught here is a threshold frequency we have. And this Ke maximum, which is equal to half mv square, that is the maximum kinetic energy of the photoelectrons which are emitted. And here m is nothing but the mass of the electron. V maximum is nothing but the maximum speed of the photoelectrons you have. So this is the Einstein's photoelectric equation. So this Einstein's electric photo equation we can write in terms of what we call stopping potential. We can write this in terms of the stopping potential we can write. So if you write this in terms of the stopping potential, the same equation you can write in terms of the stopping potential. So we know that Ke maximum in terms of stopping potential should be equals to EV naught. It should be equals to EV naught. So therefore, we can write this h nu is equals to phi plus EV naught we can write. Phi plus EV naught. So V naught is the stopping potential here we have. So if you find the V naught value from this equation, we can get it as a h nu by E minus phi by E. H nu by E minus phi by E. So this is the Einstein equation in terms of the stopping potential. In terms of the stopping potential. So this equation, whichever we have written, this V naught is equals to h nu by E minus phi by E, whichever it is there. So this relationship, whichever we have, it predicts the linear relationship between the stopping potential V naught and the frequency nu. Okay, V naught and stopping potential V naught and frequency nu. So here, this h by E, whichever we have, okay, this h by E is nothing but the slope in the linear relationship, and this minus phi by E, whichever we have, this minus phi by E will give the y-intercept it is going to be given. It is going to be gives the y-intercept. That is nothing but this equation is in the form of y is equals to mx plus C you are going to be have. So this H by E is going to be give the slope, and this y-intercept minus phi by E is going to be given. Okay, so this is what the Einstein's relation in terms of the photoelectric equation in terms of the stopping potential we have. Okay, so if you see the Einstein's photoelectric equation, otherwise this Einstein's explanation of this photoelectric effect, if you see the experimental observations, if you see experimental observations, if you see here, okay. So first thing which we have is a threshold frequency. Threshold frequency, right? So this threshold frequency, in terms of this Einstein's explanation, if you see, it should be, if suppose if you take nu is less than nu naught, okay, the incident radiation frequency is less than the threshold frequency, then what will happen? The electrons cannot escape. That means electrons will not come out from the metal surface. So always nu should be greater than nu naught. Okay, it should be more than nu naught. It should have. Okay, and one more thing which observe in the experimental observation of this Einstein is instantaneous emission. That means whenever one photon gives all its energy to one electron instantly, and it is going to be come out, right? And if you see the kinetic energy, this kinetic energy is independent of intensity. Okay, so kinetic energy, if you see, kinetic energy is independent. Okay, independent of intensity, right? So each photon has a fixed energy, as we have seen that, which is h nu. So intensity only affect the number of photons. Intensity will only affect the number of photons. And one more observation which we have is the current is proportional to the intensity. More photons means you should require more electrons ejected out. That means the incident radiation intensity, if it is more, automatically the current which is coming out, that is number of electrons which are coming out per second, will be more you are going to be have. Okay, and similarly, the kinetic energy will increases with frequency. Kinetic energy increases with frequency. So that means higher the frequency means higher the photon energy you are going to be have. So these are some experimental observations explanation we have. Okay. So for this experimental verification, okay, experimental verification for this Einstein's explanation of this photoelectric effect will be done by this what we call Millikan. So Millikan, he conducted some experiments in between year 1914 to 1916. He confirmed the relation V naught versus what we call nu. Okay, confirmed the linear relationship between the V naught and nu. And he measured the Planck's constant from the slope, which obtained value is in agreement. Okay, so he measured the Planck's constant from the slope he measured. So whatever may be the value which you got is obtained value is excellent agreement with the Planck's value you have. Okay, and Millikan had hoped to disprove the Einstein's theory, but ended up providing its strongest experimental support. Okay, actually, he did the experiment to prove that the Einstein is wrong, but whatever may be the experiments he done, he got the whatever may be the Einstein's equation has been given, the same results he has been got experimentally. Okay, so he calculated the work function values for different what we call metals he calculated. Like if you take the cesium, work function is 1.9 electron volts, you have threshold wavelength is 653, like sodium, all these cesium, sodium are alkali metals. Sodium is having what we call a 2.3 work function. Zinc is having the work function of 4.3. Copper is having the work function of 4.7. Similarly, silver is having the work function of this 4.7. So this is the experimental verification for this what we call Einstein's explanation for this photoelectric effect. Then we'll move to another effect, which we call it as a Compton effect. So this Compton effect is discovered in the year 1923 and named after him only. This Compton he discovered, so that is we call it as a Compton effect. So this Compton effect provides the what we call evidence for the particle nature of the electromagnetic radiation. Okay, it involves the scattering of X-rays by losing bound electrons in matter. Okay, so if you take the experimental observation for this Compton effect, when a monochromatic X-rays, okay, when a monochromatic X-rays, so this should be monochromatic, should have the single wavelength. Monochromatic X-rays of wavelength lambda, if you taken of wavelength lambda, when they are incident on a target material, they scatter the X-rays. Okay, so like this, they are incident on a target material. Generally, the target material will be like what we call a graphite you are going to be have. So when they are incidented, so they observed that uh, the X-rays are scattered in this manner. Okay, so one is having the unmodified radiation, means what it may be the wavelength which we have taken, which is hitting this target material graphite, and this is also having the same wavelength lambda. And another radiation which is coming out is having the modified, we'll be calling it as modified radiation, which is having a wavelength of lambda dash. Okay, so this lambda dash wavelength is longer than the original wavelength of radiation. Okay, this lambda is, this is the incident radiation which is having the wavelength of lambda, and it is coming out as same radiation which we call it as unmodified radiation, which is having the same wavelength lambda, and this is modified radiation. This is having the wavelength of lambda dash. This lambda dash is longer wavelength than the incident X-rays. So here the Compton shift is given by delta lambda. Here the Compton shift is given by delta lambda. So this delta lambda is generally written as lambda dash minus lambda. Okay, delta lambda is equals to lambda dash minus lambda you have. Okay, and moreover, this Compton shift delta lambda is generally dependent upon the scattering angle. Depends upon the scattering angle only. Theta, whichever we have, it depends upon the scattering angle theta, and it is independent of the incident wavelength and the nature of the scattering material. Nature of the scattering material and the incident wavelength, it does not depend. Only the Compton shift depend on only the scattering angle theta only, but not on the incident wavelength or the nature of the scattering material, he observed. So what are the classical theory failures which we have is, classical wave theory predicted that scattered radiation should have the same wavelength as the incident radiation. It could not explain the wavelength shift. That means whichever we have got, like a lambda minus lambda dash, whichever we have got, that does not explained by this the classical theories. Okay, so now we'll see the quantum explanation for this Compton effect. So this Compton shift here, whichever we have whichever we have written here, delta lambda is equals to lambda dash minus lambda. So generally, this delta lambda should equals to lambda minus lambda, which will be equals to h by m naught c into 1 minus cos theta. So here h is a Planck's constant, m naught is the mass which we have the electron, and the c is the velocity of light. So these all are constant values. So one is also constant, only theta value can be varied. So delta lambda shift will be depend on only theta. Okay. So delta lambda only depend on theta, and it does not depends upon the values of h and m naught c here. Okay. So this is what we have the Compton effect. Next, we will see the dual nature of light. Dual nature of light. Dual nature of light. Right. So light exhibits both the wave nature and as well as the particle nature. And particle nature. Light exhibits both wave nature and as well as the particle nature, or we can say that both wave and the particle properties it is showing. So wave nature where we observe and the particle nature where we are going to observe means this wave nature of the light we have seen. The wave nature of the light we have seen in the case of the experiments like interference. Okay. So wave nature where we observed is in the case of the interference, in the case of the diffraction, as well as in the case of the polarization. In all these cases, we say that the light is wave nature. So in the case of the Young's double slit experiment also we have seen, right? And whereas in the case of the particle nature, if you see, so this particle nature where we observe means in the case of the photoelectric effect, Compton effect, okay? Here we observe that the light is in the form of a particle nature. That means the light is having both wave nature as well as the particle nature, both it is consisting. So next, if you see the concept of matter waves, the concept of matter waves is given by de Broglie, okay, which is given by de Broglie. We call this as de Broglie hypothesis. De Broglie hypothesis, which is the concept of matter waves. Concept of matter waves. So if a light can behave like a particle, then particles means electrons like might behave like waves. Okay. Light, which initially we call it as a wave actually, which can behave like a particle, then particles means like electrons might behave like waves. So this is what proposed by the de Broglie in the year 1924. Okay. So if a light can behave like a particle, then particles might behave like waves. That means that is the concept of matter waves he proposed, de Broglie proposed in the year 1924. Okay. Suppose if you take a moving particle, so every moving particle is associated a wave. Every moving particle has an associated wave. So therefore, the wavelength of that will be taken it as a lambda. The wavelength of that is taken as a lambda. So this lambda is given by actually h by p which is equals to h by mv we are going to become. So here P is nothing but the momentum. P is nothing but momentum. V is the speed or velocity we can say. And we have the m, that is nothing but the mass. M is nothing but the mass. Okay. So this we can derive using what we call the formula this. For a photon, if you take, we know that energy should equals in the form of h nu, E is equals to h nu. So this, if you write in terms of P, if you write here, so we are going to get this will be equals to Pc. That implies P is equals to h nu by C we have. Okay, h nu by C. Otherwise, we can write it as h by lambda we can write. So de Broglie assumed that the same relation holds for material particles. Right. So next we have is experimental verification, that is a Davison and Germer experiment. So Davison and Germer, they provided that experimentally they verified the de Broglie hypothesis by observing the electron diffraction. Okay. So what is the Davison and Germer experiment tells is experimentally verified the de Broglie's hypothesis. Experimentally verify the de Broglie's hypothesis by observing what? Electron diffraction. So if you see this what we call Davison and Germer experiment here. Similarity between X-rays and the de Broglie matter waves suggested the method of experimenting on the diffraction of X-ray, which could be extended to matter wave. Okay, so the scientists Davidson and Germer, they performed the experiment in the year 1927 using a beam of electrons. Okay, using a beam of electrons instead of what we call X-rays. Okay, so instead of using the X-rays, they performed experiment by using the beam of electrons. Okay, so their apparatus, which is consisting of a tungsten filament. Okay, so this tungsten filament, which is heated electrically, so that the emitted electrons are accelerated by a variable potential difference in between them, between the filament and the plate. So they'll apply some potential difference V in between the filament and the plate, so that the electrons emerge with kinetic energy EV, okay, in the form of a fine parallel beam. Okay, so this arrangement acts as an like a electron gun. So the beam travels in free space and falls normally on a single crystal of nickel. Okay, and this entire apparatus is enclosed in a high vacuum chamber. After hitting that, the reflected electrons are collected by a detector, which is a Faraday cylinder. This cylinder is surrounded by another cylinder to which applied a retarded potential. Okay, applied a retarded potential. So this is to allow into the cylinder only those electrons whose velocity after reflection is of the same order as the velocity before reflection. Okay, so this also prevents the electrons of lower energy from entering into the tunnel, right? So the detector is set at a particular angle to the incident beam, and the readings of the intensity of the reflected beam is noted for the different values. Okay. So this is how they have performed the what we call experiment, that is a Davidson and Germer effect. Okay. So they calculated the wavelength from the formula for like a 54 electron volts, which are going to be come out as a 1.64 angstroms wavelength. So this wavelength is of the order of wavelength of X-rays. Okay. And X-rays have already given us information about the spacing of what we call atomic planes in nickel crystal. So like this they have performed, and the distance between the successive reflecting planes is obtained is given by some t is equals to 2 sine theta. If theta is 25 degrees, or means by using the formula lambda is equals to 2d sine theta, which is a Bragg's formula. So by substituting the lambda, what we call d sine theta value, that means the distance and sine theta value, they got the wavelength. They got around 1.67 angstrom. So whatever may be the values they have produced, the close agreement between the calculated or predicted and observed. Okay. So between the calculated or predicted and observed values. So wavelength of the electron beam clearly establishes that the validity of de Broglie matter wave. The validity of de Broglie matter wave. So this is what we have the what we call Davidson and Germer experiment. So then after we have like a experiment, another experiment, that is a Thomson and Reed who performed this experiment. So according to this Thomson and Reed experiment, so actually when they have performed this, after Davidson and Germer performed their experiment, after a year of performing Davidson and Germer experiment on electron beams, these Thomson and Reed they have performed by using the method of high energy electrons produced in discharge tube and maintained low pressure and subjected to the high voltages, which are around 10,000 to 60,000 volts they have applied. Okay. So in their experimental arrangement, they have an electron beam which was restricted to a narrow pencil, right? They have the electron beam which was restricted to a narrow pencil beam by means of appropriate like what we call the steps they have been taken. So the thin electrons beam is then passed through a metallic foil. So generally the foil is made up of some very microscopic crystals. Okay. So they were arranged in a random fashion and they performed this experiment. So in their experiment, whatever may be the values which they have got,